Welcome. In this video we talk about traits. Traits are Rust's approach to both inheritance as well as constraints or concepts in C++. They are not only used to organize dynamic dispatch, but also at the same time to give constraints on template arguments for template programming. There's lots of things to say about traits. In this video we will see a first example. In a later video we will talk about other things about traits. So let's dive in right away. Here I define a trait animal. It's like an interface description saying that any type which implements the trait animal has a make noise method, which has self as first mutable argument. That is, it is a method on that type and it can mutate the type. It also has an eat method, which takes one argument how much, which is an integer 64, and it has a function, a method called isHungry. That is the complete description. Now let's move on. I implement a struct dog with the usual deriving the debug stuff, and we just do something silly. We say need food and implement the three methods accordingly. Notice that we use a basic impl block, but we say we implement the interface, the trait for the struct. And then we define the methods. That is, we have made it explicit that the struct dog, the type dog, implements the trait animal. Here I have added a different method for dog, namely a constructor, just for convenience. So now I have done exactly the same for a cat. It's essentially working basically the same. It prints something else and it says cat eating and so on, such that we notice that some different behavior is happening. We also implement a constructor, and that means that we can now implement a function which takes as one argument a mutable animal. Notice this impl keyboard here. This does not yet mean dynamic dispatch. Rather, this means that this function is a templated function on some type. But this type, the only types which are allowed, are types which implement the trait animal. A different notation is given here, which we could have used. Here we just use the function notation for a templated function, and we give a trait bound for this template argument, which basically means that this template type t must implement the trait animal. Now the compiler of course can check by us knowing that, or by knowing that this type which is given for a implements the trait. We know that we can call the make noise method, we can call the isHungry, and so on, and we can organize this function here. At the call side, we can simply create a dog and call the live function template, or we can create a cat and we can call the live function template as well, and the compiler will just create two different instances of this templated function. Let's see this in action. Indeed, we have a dog which barks and a cat which meows. In the second example, I want to make this point a bit more about template functions. It's exactly the same for the dog and exactly the same for the cat. But let me notice that this is a standard argument here, so it has been moved inside the live function. Therefore, if I now want to move on with a different function, I have to recreate the objects because here they have been moved into this template function. I use new brackets here such that I can easily distinguish between the types. So here I create a new dog and a new mutable cat, and this time I call a function which takes two arguments and I just hand in references. Now, as you can see, the first argument here is a dog and the second is a cat. Now let's look at this party function. I've defined it in this way here. I've given it two template parameters, and I use the where notation to say that both these template arguments need to be animals, so they need to implement the animal trait. Why am I using two? Well, if I give two such template arguments, then the two template parameters can be instantiated to different types, even though they both implement the animal type. And that is exactly what I want. So first of all, I wanted to show you this where notation, which is quite convenient if you have more complicated trait annotations here. And secondly, this is the right thing if you actually want two different types as this argument here. And there's nothing special here. We just call the methods, but we have whatever types are there. Now let's look at alternatives. If I would have taken the first notation here, I would have basically used the shorthand notation with impl animal. But if I do this, the compiler complains. Why is that? Well, by definition, if you use just impl, it's the same as having a single type parameter, animal, with a trait bound, and then having the same types here. Yeah, and this is not what we mean, because we want to call it with two different types. So therefore, the only alternative notation which would have worked is this one here, where we explicitly give here two trait bounds and take two different template parameters. But then, of course, I have to remove the where here. So that is a possible notation. What is going on now? Unclosed. This has to go as well. So this is a possibility to denote things. That is, we can just use the trait bound with every template argument separately. Or, which I would probably prefer here, is the original one, where I use the where notation. So between the list of the arguments and the possible return type and the actual implementation, you just put where and give your trait bounds. That's easier to read when the trait bounds are more complicated. So let's try to run this. So indeed, in the second part here, we have a party of a cat and of a dog. In the next example, we want to actually use dynamic dispatch or a vtable. Let's look at the program at the top level. Here I get the command line arguments as before, and then I declare a so-called box dyn animal. This dyn keyword here says that it's dynamic. So here I actually have a box which is just a smart pointer, where I have a smart pointer to something which implements the animal trait. So this is now actually determined at runtime. Notice that when we were using the impl keyword earlier, we were actually just doing template functions such that the compiler can generate the correct code for the correct type for each case automatically. Here, the compiler has to generate code before knowing what actual type arises. So now it's a runtime thing. And therefore, we have to use this interaction with a pointer or with a box here, because the compiler at compile time cannot know how much memory the type needs. Therefore, we need this interaction. So what I do here, if the first argument, if there's not a second first argument, then it breaks. If the first argument is cat, it creates a cat. Yeah, here I take the cat constructor and put it into a box. That is, it's allocated on the heap, and I just return the smart pointer. And if the argument is dog, then I create a dog. And then I call my live function. Now, for this to work, I need to make sure that the argument live takes is a smart pointer to a dyn animal. Yeah. In that case, I can move my smart pointer into the function here. And the function can be compiled once and for all and work with any such type. Obviously, behind the scenes, it does what C++ would do in case of inheritance. It would create a virtual table and not only hand in the pointer, but also the v table. Let's see how this works. If I give no argument, I get an error. If I give dog, I get something which barks. If I give cat, I get something which meows. Dynamic dispatch at work. Finally, I want to show you that we can also use dynamic arguments for return types. The program is essentially unchanged, except that here I give the smart pointer, I work with it, and then I just return it again. So here I've just said that the return value of this function is also a box-dyn animal. I just hand out the pointer again. Now, this program here takes the a which we made and moves it into the lib function, takes the result out and assigns that to b, such that we can also call it outside. Notice that if I would have used a again, I get a compile error because the value a is moved. The smart pointer has been moved into the lib function and the return value has been moved out again, such that I can use it here. We haven't talked about smart pointers, but needless to say, the pointer is automatically dereferenced and I can just use the dot notation as if it would be the object itself. Let me run this. Cargo run. Dog, yeah, it barks, and cat, it meows. Notice the double bark and double meow here. That is the outside operation on the b, which we have down here that make noise. The purpose of this video was to show you the two uses of traits. One as trait bounds for template arguments, and second for dynamic dispatch similar to inheritance. We will see lots of more things with traits because they are an important concept in Rust, but for today's video it's enough. See you in the next one.